Okay, so now we're going to continue with the end of chapter section 4.1. So in this section, we're still in section 4.1, and we are going to talk about the superposition principle. Okay. I mean, we now have Abel's theorem, and states the theorem of this section, which the proof will be, let's say, the proof of this theorem would be in a model. You can take a look at the proof. Okay. Theorem is the following. Given a linear homogeneous ODE of order n, which is an of x yn plus a0 of x y equal to 0, with a1 up to an continuous in I, and an of x is different than 0 for all x and I, then there exist n linearly independent solution y1, y2 up to yn to the ODE. So it's n solution. So if I have a linear, so I have an ODE of order n, I can have n linear independent solution. Moreover, the set y1, y2 up to yn, once I have n independent solution, generates all the other solution. That is, every solution to star, let's call this ODE star, to star can be written as a linear combination of y1 to yn. That is, the general solution to star is y, you should call it yc. It's called because solution to homogeneous equation is c1 y1 plus c2 y2. Well, let's keep it y now, we don't have a reason. Plus c3 y3 plus cn yn. And this is the answer to our question. But we say that y1 up to yn is a fundamental set. Some properties of fundamental set. So the number of functions in the fundamental set is the same as the order of the equation, is the same as the order of the equation. So if order 3, I should have three functions in the fundamental set. Not two functions. Even if the two functions are linearly independent, the second thing should be that they should be y1 up to yn should be linearly independent. So if it's not like if order 3, then on any three function are a fundamental set. No, the three functions should be linearly independent. Okay. A remark. Fundamental sets are not unique. Okay. Well, this is something like example, and let's give an example. Okay. So find the general solution. Well, find fundamental sets of the ODE y double prime plus y equal to 0. So solution, I already know that sine x, cosine x are two linear independent solutions, and they are two functions, so this is a fundamental set. What about 2 sine x minus cosine x? These are still two solutions and they are linear independent. What about sine of x plus 3 sine of x? These are linearly independent, by the way. You can prove they are independent because sine x plus 3, well, I think cosine x plus 3. This is what we proved. We proved that cosine x plus 3 is a solution. So let's cosine x plus 3 cosine x minus sine x plus 3 minus sine x. Let's check they are independent. So you get minus sine x cosine x plus 3 plus cosine x sine x plus 3, and this is equal. So I have cosine A sine B. So this is cosine A sine B minus sine A cosine B. So this is well, sine of B minus A. So this is cosine of x, well, sine of x minus x plus 3. You agree? Sine of x plus, wait, it's sine x plus 3. So this is sine A, this is cosine B, this is cosine A, this is sine B. So this is sine A minus B. So this is sine of x plus 3 minus x, which is equal to sine 3, which is different than 0. Then they are linearly independent, and they are two functions. What about sine x? This is not a fundamental set. I should have two functions. What about sine x cosine 2 sine x? This is not a fundamental set because these two functions are linearly independent. What about sine x cosine x and sine 2x? These are not, because they are three functions and the order is 2. What about sine x e to the x? Well, these two are linearly independent, but e to the x is not a solution. So this is wrong, okay? So maybe the number of functions should be the same. Here n should be linearly independent, and yn up to yn are solution. It's not I'm choosing any functions. Okay? And this is our answer to this is the answer to, like if I have a solution of order 2, then it's enough to find two linearly independent solutions to generate all the solution. Okay? So similarly, you can check that e to the x, e to the x, and 1 are linearly independent solution to the ODE y triple prime minus 2y second plus y prime equal to 0. This I already did this one. So 2, so this is done. Find the general solution to the ODE. The general solution to the ODE. Well, I have three linearly independent solutions, so to generate all the solutions, so the general solution is C1 times 1 plus C2 times e to the x plus C3 x e to the x. So the fundamental set somehow generates the space of my solution. Now, the superposition principle in the case, in the non-homogeneous case. So what is the general solution looks like? Or for y double prime plus y equal to x. Okay. So how do I solve this one? So now, suppose I can find, guess, or you should wait till section 4.3, 4.6, 4.8, one solution to y double prime plus y equal to x. I could able to guess one solution, okay? Call it yp. This means L of yp is equal to x. You agree? Then let y be the general solution. How to find all the solutions? The general solution to L of y equal to x. This implies what? That L of y minus yp by linearity, this is L of y, is equal L of y minus L of yp. And this is equal to L of y is x, L of yp is x, equal to 0. This means y minus yp is a solution to the homogeneous equation. Right? But I know that the homogeneous equation, which means y minus yp, in this case, which is y double prime plus y, is c1 cosine x plus c2 sine x. And this implies that y is c1 cosine x plus c2 sine x. This is the homogeneous solution, which is denoted in the book by y sub c, plus yp, that is a particular solution. Now, can you guess a solution to y double prime plus y equal x? You can guess that by guessing. You can see that yp equal to x. Yes, if you plug in x, I mean, you get, if you differentiate x twice, you get 0. So if the function x is a solution to y double prime plus y, so guess yp equal x is a particular solution. And this implies that y equals c1 cosine x plus c2 sine x plus x is the general, is a particular solution, is the general solution. I'm going to use this proposition principle a lot in section 4.6, 4.6, 4.4, 4.6, I guess. What did I say here? 4. No, this is 4.4, 4.6, yes. So the theorem, or the principle, given a linear ODE of order n, which is of the form an of x yn plus 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 a0 x y equal f of x, let yc be the solution, be the general solution to L of y equal to 0, and yp a particular solution to L of y equal f of x. I found one solution, and I know the general solution to the homogeneous equation. This implies that the general solution to star is y equal yc plus yp. But how do I find yc? This yc is c1 y1 plus c2 y2 plus 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 cn yn plus yp, where y1 up to yn a fundamental set to L of y equal to 0. So please, here I need an of x different than 0 for all x and I, and a0 up to an and f are continuous. Okay, these are the conditions. And this is the superposition principle for linear non-homogeneous equation. And this is the end of section 4.1.